Ready for me to start? All right. First of all, thank you everyone for taking the time to join me. It's a pleasure to be up here talking about MLCommons. As the slide says, I'm the executive director, one of the founders of it. So we're going to talk about what we do to make machine learning better for everyone through benchmarks and data. Please leave your heckling and tomatoes until the end, and then we can handle them. So let's get started. This is me, not super interesting, not what you're here for. So I'm going to start with just an overview of the organization and our mission. A while back, when we were starting out, we looked around and we realized that there are a lot of open engineering organizations like IEEE, SPEC, if you're familiar with computer benchmarking, TPC, and there are also a lot of AI organizations, but most of them actually don't do joint collaborative engineering. So if you look at like the Partnership on AI, they're very policy focused. And you know, our mission is really, as the Venn diagram suggests, we want to be doing collective engineering across the industry, across academia, very focused on AI and machine learning. We're a global community. We have over 50 member companies on 6 different continents. If anyone here is from a company or an organization in Antarctica, please see me afterwards. I'm tired of saying 6 continents. We're always looking to expand our reach, and maybe one day we'll get a moon base too. But you can see we have folks from all over who came together to work on things that are valuable for the whole industry. And actually, the founding of the company dates back to some of the early Databricks days. Matai was one of the people who got started on some of the seminal work in MLCommons. And so we have researchers from all over, and it really did start out as a collaboration between industry and academia, and that tradition carries forward. So our mission is building better machine learning for everyone. And we kind of accomplish this through 3 pillars. Benchmarks and datasets, which are really the focus of this talk, as well as best practices. And underlying all of this is research, right? Machine learning and AI is such a rapidly growing area that, you know, the shift from research to development to practice can be really rapid. And so if we want to stay abreast of what is going on in the machine learning world, we really do need to tap into research and have our eyes and ears open, right? You know, everyone's obsessed with generative AI, but if you rewind a few years ago, GANs were a thing, but you know, they never really made it to prime time, right? Now you look today, stable diffusion is much more heavily used, right, at least for image generation. As for why that is, you're probably better off asking someone in my organization. But if you do not stay on top of the research, things will change under you so fast. So why did we pick benchmarks? This is a little bit of a kind of TED Talk high-level piece, but if you look at some of the seminal work that is behind folks like OpenAI, this is from a paper at Baidu Research out of Andrew Ng's group, and what he's really highlighting is that if you don't have a lot of data, AI and ML doesn't really help, right? And this was the case, you know, in the 80s and the 70s and some of the early AI periods, right? But once you do get a lot of data, you get into this nonlinear regime in the middle, right? And the thing that's important here is the x and y axis or log scale, right? These are not linear axes, and also this is a conceptual plot. But what it's saying is that when you get enough data, right, and you start using more advanced ML techniques, you start really rapidly improving your accuracy. And somewhere along those curves are these qualitative inflection points. And it might be we get self-driving cars, it might be you know, the AlexNet moment when we realize computers are better at image recognition than, you know, the normal human threshold. But along this curve is always going to be these points where AI brings us sort of previously magical capabilities. And so as we get more data, we drive along this curve and bring more capabilities into everyone's hands. Well, if you need big data to make this happen, you also need big models, right? So this is some work out of Berkeley. The RISE lab showing trends in the parameter size and count for various models. And for those of you who are kind of from a hardware background, as I am, 2x every 2 years doesn't sound bad, right? That's Moore's law. But when you see a number up there like 240x every 2 years, that starts to get really scary, right? And so we need more performance. Now, that also means we need more compute. If you have a lot of data and you have a large model, you need a lot of compute, right? And I think the real thing I'd point out is if you look at the compute that it takes to train models, and this was done before the chinchilla scaling laws, so things might be a little bit different, but not substantially different. The key point here is if you look at the numbers for transformer-based models up there, that's 750x every 2 years. So that's actually, the compute is growing faster than the parameter count or the data. And so that's a really scary trend, but that's something that we want to tackle. So this leads to something I call the fundamental theorem of machine learning. I studied math, so this is kind of a riff on the fundamental theorem of calculus, if you remember that. This is also very high-level napkin math that you can use at a TED Talk, right? And it's basically big data plus a big model plus big compute equals innovation, right? This is this kind of thing you show at a TED Talk and everyone's really impressed, right? But the prior slides are really the money slides. And that's talking about training, right? And training is the process of finding the thing that is magic, and inference is about how do you use it, how do you deploy it, right? Inference is challenging for a different reason, and it has to do with scale. Facebook said that they've got about 3.5 billion users as of a few years ago, and that translates into over 200 trillion inferences per day. That's a lot. I think I did the math, that's 2.3 billion inferences per second across all of Facebook's data centers. Now that's probably grown. These numbers are a couple years old from my friend Kim Hazelwood. I'm sure it's even more today, and you have to do that at low latency, right? Now, the latency is actually really important, especially as you start talking about certain other applications. Just some more rough napkin math. In the automobile world, a car can go about 100 feet per second, right? And so you can actually equate latency to feet of displacement in the car, and that tells you how fast you might want to be going in a car that is under computer control. And so you have about 50 milliseconds for inference in a car, for example. All right, so those are some of the performance challenges. How are we going to tackle them? How do benchmarks play a role? Benchmarks are really about progress and transparency. Famous quote from Peter Drucker, what gets measured gets improved. If any of you have OKRs at work, you know what people mean by this. There's a secondary function of a benchmark, particularly an industry standard benchmark, which is it's about aligning everyone on what does it mean to be better, right? Imagine for a moment you're buying a car and one guy comes up to you and says, I can go 300 miles an hour. Next guy says, I can cut a corner in a quarter of a second. And the last guy says, I have airbags. Which car do you pick? Like, they're not talking about the same thing, right? They're all talking about the value they provide, but it's measured in a different way. Now, I live in San Francisco, so going 300 miles an hour is a very academic exercise, and I'd rather have the airbags, or perhaps even better, unbreakable windows. Right? But the point is, when you align everyone on what it means to be better, you get to go a lot faster. And benchmarks aren't perfect, but the key is how do we point the industry in the right direction so we're all working together and going fast. I never rowed crew, but the key point of rowing crew is you all have to be in time and in beat, and that's how you win. And that's what we want to do for the industry. So when we look at benchmarking ML systems, which is how we got started with the MLPerf benchmarks, this is what we're trying to do. I'm not going to read off the whole slide, but I will point out some of the most important things. You want a benchmark to be generalizable. You want it to be fair. You want it to be rigorous and reproducible. You don't want to come up with some sort of performance number that your vendor shows you and then you can't reproduce. And we want to push the whole industry forward and pick the right things to focus on. Now, ML is nice because it's a full system problem. And I told you, hey, we need to boost compute performance by 750x a year. That's really hard. The great news is we have a lot of different levers to pull to get that performance, right? So you can talk about data optimizations. So for instance, when you're talking about training a large language model, a lot of times the strings you're feeding in have different length. If you sort those strings and bucket them by similar length, you will increase the utilization of vector units, and that can boost your performance by a factor of 2. That's a technique that one of our member companies showed off in the MLPerf benchmarks and is now used as sort of as a standard procedure in the industry. So that's an example of how benchmarks can help drive performance for the whole industry and benefit the community. We get faster silicon thanks to our friends at Intel and TSMC. We get more advanced architectures that boost performance. You get better algorithms for training. So, many people know that in ML training, you might use something like stochastic gradient descent. More recently, we're seeing a lot of people use second moment or adaptive optimizers like Atom, right? And that lets you scale up training to bigger systems. Scale, of course, is another factor here. When people start talking about things like GPT-3, we actually have a GPT-3 benchmark that came out Tuesday, that was trained on systems with up to 3,500 accelerators. So building out larger scale systems gives us more performance, and then just general software improvements. If you come up with a better FFT optimization, faster compilers, all of those things help. And so for MLPerf, which is our main benchmark suite, these are some of our goals. We want reproducible results, representative workloads, fair and useful measurement, and we want to serve both the commercial and the research community. So MLPerf is a suite of benchmarks. I like to joke it goes from microwatts to megawatts. Microwatts is represented by our Tiny suite, which measures inference performance on IoT devices and microcontrollers, so things like keyword spotting, for example, all the way up to our HPC benchmark suite, which someone ran on half of Fugaku. For those who don't know, Fugaku used to be the world's #1 supercomputer and I think is now still in the top 5. But it burns 20 megawatts and we ran on half of it. So in addition to having the breadth of benchmarks that you see up here, we've also improved them. We have some standard techniques to improve convergence for training benchmarks. We added throughput as a metric for HPC systems because many of those are multi-user rather than single jobs. Something I personally led was doing power measurement for inference. Right? There's definitely been a lot of talk lately about the environmental impact of ML. And having industry standard power measurement helps us to get a handle on that and then optimize it. And soon we will have power measurement for training as well. This is a look at the MLPerf training 3.0 suite, something this came out 2 days ago, so very hot off the press. We added a large language model benchmark using GPT-3. And then we have a new recommender benchmark that is a multi-hot data set based off the Criteo 1 terabyte data set using a DLRM style model. So this came out pretty recently. And you'll notice we have a great assortment of both data types here, as well as different networks and different application areas. But they do all use open data sets that are pretty easy to get. This was not the slide I expected. No. So this is, if you look at the results of our latest MLPerf training that came out a little bit earlier, you can see the performance that we are getting. I normalized all of the benchmarks over time, and for those that we added a little bit later on, I normalized them to Moore's law. And I think the key point here is that the MLPerf benchmarks help to drive the industry forward, and they're also a barometer on progress. And what you can see here is that in terms of performance, we're actually doing a lot better than Moore's Law. For some of these benchmarks, it might be a factor of 3, it might be a factor of 10, but we're helping to get more performance into the hands of ML researchers and experts. I had to convert this from Google Slides to PowerPoint, and some of the conversion didn't go quite so well. So there you go. And again, this is relying on those levers that we had before, system scale, new architectures, et cetera, to drive better and better performance. So that's sort of the benchmark side. What have we done to help drive performance for the industry, and how can we help? I want to talk about data sets a bit, and data more generally, which is really the lifeblood of ML. Many of you may have heard Andrej Karpathy's Software 2.0 analogy that a lot of other folks have picked up. You know, ML is the new version of software. Well, let's explore that a little bit more. So if you follow that metaphor, data is the new code. So data defines your best possible functionality. If I have training data for a car and I have no data from the snow, when I build that automated self-driving system, it's not going to know how to handle the snow, right? So data is going to define what is possible. The model takes this data and, much like a compiler, transforms it into a program. Now, the difference between a compiler and a model is compilers are minorly buggy, but you know, a model is intrinsically imperfect, right? So the transformation is lossy. So one of the things that this means is, you know, when in the 80s, when we wanted to build programs, you had to load up on developers, build a program, and test it. That's true today, but again, follow the metaphor, right? Now we have to build data sets. And building data sets is actually in some ways harder than code. The risk of bad data is very significant. So if you want to start training a model, you're going to ask yourself questions like, what data do you have? What data should I get? Are there errors in my data set already or in my labeling? How do I keep costs down? So, you know, maybe I have some important data inside my enterprise and I want to figure out what I should be labeling, right? Picking the right thing to label is really important. So there's a lot of problems that you inherit. And now a really big one is, forget about the training, right? What about the test? You know, you can write a test as a software developer. You know, you have test-driven development. That's a very common thing. In ML, right, data is going to define your tests. So we already talked about how training data can sometimes have problems. It's way worse if your test data has problems. So does anyone know what this picture is? Any guesses in the audience?
I don't remember the bridge, but it resonated with people.
Yeah. All right, so I'm going to repeat the answer for our folks in the back who are recording this. So that's the Tacoma Narrows Bridge. I'm from Seattle, Washington, which is just around the corner from Tacoma. So when they built this bridge, they didn't really model the full effects of the wind. Turns out the winds got really high and basically shook the bridge apart, in part because, as the gentleman up front, Timothy, said, it induced waves in the bridge that started reinforcing and superimposing on itself, and the bridge just shook itself apart. So they didn't have training, they didn't have test data to test for that case. Boom, your bridge breaks apart. So if you have problems in your test data, you know, hopefully you aren't designing a bridge, right? But this really illustrates the point, which is that if you are missing critical data from your testing suite, you will not know when you have a problem. Right? And you know, it's one thing to introduce an error. Mistakes happen all the time. People are people, right? But when you don't know you have an error, that's really bad. So one of the things that's actually really critical here is, so first of all, most companies make money from internal data, but a lot of the progress that we get is actually driven by public data. So my friend and colleague Vijay Reddy is a professor at Harvard. He surveyed years of ML papers. And what he found is that, as you can see up here, about 80% of the papers cited open data sets. And this includes papers from folks at Google Research, at Facebook, at all the major AI players who have massive internal data sets. But they're always citing open data sets because one of the fundamental principles of science is you need to be able to reproduce it, right? And you can't reproduce experiments with third parties on your proprietary data. So that's why we use open data sets, and they're critically important for the ecosystem, right? Imagenet is the thing that provided us the baseline that allowed us to say at some point that AlexNet beat humans at computer vision. And so what we really want to do when I look at where the industry needs to go is we need to start this virtuous cycle, right? If we get easy to use, easy to share public data sets, that lets us run experiments publicly to compare our notes, to make better benchmarks, which then lets us make better data sets, right? And you're going to go through this loop internally when you're developing a model, but some of this needs to be done publicly for the whole industry. I talked a little bit about Imagenet and AlexNet before. So, you know, in a lot of ways, the last decade or so of ML was very much driven by advances like Imagenet, right? And Imagenet was about a $300,000 project, put together a bunch of labeled images, and you know, sooner or later we had enough folks banging their head against Imagenet, and we realized that using deep learning, we could beat humans at image recognition. All of a sudden, folks saw, hey, there's commercial potential here, and you know, a decade or so later, you know, out comes LLMs and all sorts of other things that are, you know, frankly fantastical compared to state of the art in 2010. So Imagenet was great, but what we want is a better version of Imagenet across many different data domains. So if you look at a lot of the public data sets today, they're pretty small. They often have legal restrictions. Imagenet's a great example of this. You would never want to use that data for something in production. The legality of the use of that data is extremely questionable, and I know because I've spent a bunch of time looking into that. If it's legally encumbered, it makes it really hard to do experiments and compare them with folks. It's certainly not redistributable, and as many people have pointed out, you know, a lot of data tends to have a developed nation bias, right? So it's not super representative either. It's not very diverse. And a lot of these data sets are static. Or if they're not static, they're dynamic in a way that's very frustrating, and pieces of the data set disappear over time, right? And if your baselines are disappearing, it's really hard to make good measurements. So what we want to do, and what we think the industry needs, is we want large data sets that are more comparable to what you'd actually use in production, right? We want them to be licensed under a commercially friendly license, like the Creative Commons family. We want it to be redistributable. We'd love for them to be diverse. We want to continuously improve them. And then one of the other things here is that as we see sort of more regulatory attention being paid to machine learning, we'd also like these data sets to be potentially useful for regulation. Right? Regulation is not a four-letter word. You know, I'm going to go back to my automotive analogy. If you think about doing lane keeping, how many folks in the room have driven a car that has automatic lane keeping? Show of hands? Like one person? Two people? Okay, two people. And either the rest of you are asleep or haven't got to use automatic lane keeping. So, you know, in theory, it's going to keep you within the lane markers. And most of the time, it's pretty good. I was actually in New Zealand on holiday late last year. I got to use the first car that I'd ever driven with automatic lane keeping, and it was mostly good. But some of the lane markers disappeared, and then, you know, the lane keeping doesn't work great. At some point, I would love to have an indicator of the quality of that lane keeping. Does it work in the snow, right? A lot of things that work on vision sensors are not going to do great in the snow and other weird conditions. And that's something that at some point, you know, even from a self-regulation standpoint, the automotive industry might want to have like, hey, this lane keeping works in snow, right? That's something that a consumer might want to know. Similarly, if you look in San Francisco, we've got Cruise, we've got Waymo moving their cars around, and they have different restrictions. Sometimes it's an area restriction, sometimes it's a speed restriction. All of those are there for safety. And, again, that's regulation. It might be self-regulation, but ultimately, data sets can help drive that in the ML space. So one of our goals is to build better data sets. And I've got 3 examples I'm going to run through that we've done. The first is called the people's speech, and it's a very large 30,000 plus hours of transcribed English speech. It's got diverse speakers and diverse speaking conditions. Right now you're hearing my voice hopefully pretty clearly through a great microphone system. But, if you go out onto the showcase floor, you're going to hear a lot of bounces, reflections, ambient noise. That's what a lot of speech sounds like. So if you wanted a data set and you wanted to actually train a speech recognition system, you'd ideally want some noise, right? You don't want just pristine podcasts. And so we got a lot of nice, diverse data in here. And we also did it for a fantastically low amount of money. I think we spent maybe on the order of $30,000 or $50,000. And a lot of that was we very cleverly used a technique called forced alignment to do semi-supervised learning. So we scraped the internet, found nicely licensed things, and then made the transcripts align with the audio, generated the timestamps, and then we trained some networks on it to show that it worked. Pretty cool. We also have one called the Multilingual Spoken Words Corpus. It's a bit more of a mouthful. This is keyword spotting in 50 different languages. 46 of those languages had no free publicly available data set in them previously. And we all know that English has pretty good coverage in most speech-to-text systems. Mandarin does, Spanish does. But after that, things fall off pretty quickly. Ukrainian has 30 million speakers or so. We were the first people to put out a keyword spotting data set in Ukrainian, right? And 30 million people is not a small number of people. So by putting out these data sets, by making them freely available, our hope is that, first of all, we'll see better research. And if someone wants to pick it up and use it to make a product, that's great. My goal is to move the industry forward. And then some of the work that I'm most jazzed about, we published at NeurIPS last year called the Dollar Street data set. And one of the things I alluded to is that a lot of data comes from sort of the more developed world. And this was an experiment in showing the power of data to help combat bias. So if you don't have diverse data, then the systems that you train on that data will lack sensitivity, right? And that's what people talk about in terms of data bias. And in general, underrepresented people, underrepresented regions tend to suffer the most from bias. And so what we did is we built a very diverse visual data set of household objects. So on the right here, you can see what a stove looks like in different geographies at different household income levels. Now, most of you guys probably make a fair bit of money and live in advanced countries, and your stoves probably look pretty similar to that Denmark household on the lower right, speaker's lower left side, that makes about $5,000 a month, right? It's a nice 4-burner stove. You'd walk into any house and know immediately what it is. And if you said, what's a stove? Anyone from the States would point at that and say, that guy's a stove. But now look in the other corner at Burundi, right? $26 a month in that household. That stove doesn't look anything like Denmark or Guatemala, right? That's a hearth, right? And so if you were to ask most image recognition systems what a stove is, they're going to catch the Denmark case. They will not catch the Burundi case. So we built this really nice diverse data set, and we were able to improve accuracy on image recognition in household objects for the lowest income quintile from 18%, which is absolutely terrible, up to 70%, which is actually pretty darn good. And so we retrained probably a handful, I think 4 or 5 different image recognition networks on our data set, and again, boosted performance by 50 percentage points absolute, right? That's just a testament to the power of data. And again, this data set is freely available, and you can go and download it. So I'm going to close with a thought and a question on where we might be going. So I talked about benchmarking for performance and how that can help to drive compute capabilities. And certainly in industry and in academia, people are used to benchmarking models, right? My model can hit this perplexity or this top 1 image recognition, right? What about benchmarking data? Right, so if we look at MLPerf, which is a widely accepted benchmark for ML systems, you freeze the data, you freeze the model, and then you start playing around with different parameters of the system. Maybe you upgrade to a new generation of hardware, maybe you build a bigger system, maybe you change the software. You upgrade from TensorFlow 1 to 2, who knows? But you change your performance by adjusting the system. All right, and so that's MLPerf. That's the benchmark that led to the birth of MLCommons and is one of our most popular benchmarks to date. All right, so let's now talk about benchmarking models. So what happens if we freeze the data, freeze the system, and change the model? What do you get? Any guesses in the audience? I'm trying to make this less boring and more interactive. Anyone? Right. Right, so you get a way of measuring the model in terms of accuracy. Is there a company that anyone knows of that does this? It might start with a K and rhyme with snaggle. There we go, okay, yeah, Kaggle, right? So if we want to do benchmarks for models, that's what Kaggle does, right? You freeze the system, freeze the data, and then you start manipulating the model to maximize performance. Okay. So, this is a diagram. I've got 3 boxes. I shifted the colors around. You can guess what's coming next. Okay, let's talk about benchmarks for data. So we're going to freeze the model. We're going to freeze the system. And now we're going to start manipulating the data. So I'm not even going to ask you what this is called because there is no one who's doing anything like that. So we started thinking about this, and we're like, okay, well, that's kind of like Kaggle, but maybe we should, yeah, there we go. Okay, it's Daggle. No, seriously, we decided that was a terrible name. It just sounds awful. So we decided to change the name. It's called DataPerf. So the core idea of DataPerf is freeze a bunch of models, freeze the system it's on, but change up the data. So you could think of for a vision system, maybe you want to do different flips and reflections, maybe you want to corrupt the image data in different ways to test robustness, but how can you manipulate the data set and the data pipeline to boost accuracy of that model? It's an interesting question. We set up the DataPerf competition. I think it was at ICML last year. And so we're actually open for submissions, and we'll be doing rounds again. But the core idea here is we fundamentally believe that machine learning is really data-centric. And so if we want to push in that direction, we should be making data benchmarks. So I want to close by inviting everyone who hopefully enjoyed my talk, and even those who didn't enjoy my talk, to come join us. And if you didn't enjoy my talk, you should just give me suggestions afterwards. So MLCommons is an open collaboration. We've got members, as I said, across 6 out of the 7 continents. We're a very friendly group of folks. We have people from so many different companies, from different research institutions, all across the globe. If any of this speaks to you, if any of this sounds interesting, if it aligns with your research, aligns with your work, sounds fun to do in your spare time, please come and get involved. You can talk to me afterwards. You can join working groups. Whatever it is, we're going to have a community event here in the Bay Area in July. So lots of opportunities to get involved, and that's my call to action. And so at this point, I think we're going to take questions.